The reason we've spent so much time on Fourier transforms in one dimension is that the generalization to higher dimensions is really pretty straightforward, and all of the properties that we derived in 1D are also valid in 2D and 3D. So in this lecture, I'm going to talk about the extension to 2 dimensions and briefly mention 3 dimensions. The 2D Fourier transform, of course, is very important for our image processing. But before we do that, let me talk about the homework problem that I gave you last time. And in fact, I'm going to do a simplified version of it. I'm going to let that parameter a be equal to 1 and just ask, what happens if we convolve a Gaussian with a Gaussian? So physically, we draw a picture of the situation. Suppose we have a signal that is a delta function, and we pass it through a filter that has a kernel that's a Gaussian. And then we pass it through another filter whose kernel is a Gaussian. And then the question is, what is the signal that we get out? So we know how to do this. So if we say that that G is one of these Gaussian functions, and H is another one of these Gaussian functions, we can solve for this using Fourier transforms pretty straightforwardly. So we know then that this transforms to G, which is e to the minus pi u squared. And this transforms to the same kind of thing. H is e to the minus pi u squared. And we know that this output, which we'll call f of x, its transform is gotten by the product of G times H. So if I do an inverse Fourier transform on that, I will get the answer that I'm looking for. Okay, so G times H is just going to be e to the minus pi u squared, e to the minus pi, let's just say 2u squared, because we're multiplying two of these exponentials together. And this is not in a form that we recognize. A better form to write it would be to say that, well, this is e to the minus pi. We'll call this bu quantity squared, where b is the square root of 2. So now the inverse Fourier transform of this, if we use the scaling rules again, that then says that my function that I wanted, G convolved with H, is going to be 1 over b e to the minus pi x over b squared. And that's my answer. So what does this look like? So here's one of my Gaussians that I started with. Let's say that this is G of x. And it's just e to the minus pi x squared. The G star H is a little bit smaller. It's smaller by a factor of the square root of 2. And it's broader. It's broader by the factor of the square root of 2. So it's going to look like this. So here's G star H. So the thing that's a little bit counterintuitive about this is that we operated with 2 filters, each with a width of nominally 1 unit. And what we got out was not a signal that was 2 units wide, but it's just a square root of 2 units wide. So so if we say that this has a width of 1, then this thing has a width of square root of 2, about 1.4. This is related in a deep way to the whole idea in statistics that variances add. But anyway, this gives you an idea of what repeated filtering might do to a signal and how you can use the things that we know about Fourier transforms to compute a convolution straightforwardly. Okay, so now to the content that I really wanted to talk about this time. And so I am now going to do the same trick that I did with the 1D Fourier transform. I'm going to try to construct a two-dimensional function out of individual cosine waves. But in this case, there are two-dimensional cosine waves, and so so the terms that I'm adding together are something like this. So this is a cosine that has one period in the x direction and is constant in the y direction. And what I'm going to do is I'm going to sum together a bunch of cosine waves like this that are different numbers of cycles and are also oriented at different angles. And I'm going to sum them up and hopefully reconstruct that two-dimensional Gaussian function. So I have here a quadrant of what turns out to be the Fourier transform of my g function. And so as I plot these points, what I'm doing is I am taking a component, in this case with 2 cycles per the entire width, scaling it by an amount that is indicated by the gray level there, and adding it up and adding them into my final function there. There's not a lot to be seen, but here you can see I have a cosine with 4 cycles running across. Now I've added in some more components, and I'm sort of getting there. I'm adding in some more components. And finally, I have a pretty good reproduction of my original function. This is a projection along the x-axis of that function. So you can see I've reconstructed a nice Gaussian that looks indistinguishable from the first one. And I did this with about 25 numbers. I constructed then a two-dimensional Gaussian using 25 coefficients. So the way I knew which coefficients to use, of course, was I made use of the 2D Fourier transform. And you can see that this is really, really similar to the 1D Fourier transform that we talked about so much last time. We have a g function that's a function of 2 variables. We have its transform that's the function of 2 variables. And the only thing that's different is that we integrate over each of those variables. And now up here in this exponent, we don't have just ux, but we also have vy. Okay, so let's look at some Fourier transform pairs. And I'm not going to prove all of these because the proofs are really really very similar to what we did last time. So this is just going to be my table of Fourier transform pairs. And so what I just showed you, demonstrated to you here is this, that if I have a two-dimensional Gaussian function, which looks like this, it transforms into a two-dimensional Gaussian function like that. Two-dimensional Gaussian, and so you can see that this is very similar to what we did before. Another function that we used last time was the rect function. Remember, it's this function which in one dimension looks like this. It goes from -1/2 to 1/2. It has the value of 1. So this is rect of x as a function of x. So we can do the same thing in 2 dimensions. We will define a square region in the plane. So this will be rect of x multiplied by rect of y. And you remember that the Fourier transform of the rect function is this horrendous thing that looks like this. It has zeros at every unit interval, and it goes by the name of the sinc function, which is sine of pi u divided by pi u. There are two definitions of the sinc function in the literature, and this is the one I'm using here. And so it turns out that the Fourier transform of the square rect is a square sinc function. That is, it's going to be sinc of u times sinc of v. So we don't have big surprises here yet. Now you could say, well, I don't want a square. I want to see what is the Fourier transform of a disk. So I can define a function called the circ function. It only depends on radius, and what it is, it's a function in the xy plane where inside this disk the value is 1. Circ equal to 1, and outside it's 0. So circ of our transforms into another function that has ripples. It happens to be a Bessel function, j1 of 2 pi rho divided by rho. And in both of these cases, what I'm doing is I'm saying that r is just the radius, x squared plus y squared, square root, and rho is the corresponding radius in the UV plane. So that's how I'm defining r and rho. Now last time, or 2 times ago, we talked about how to make a limit of a limitingly narrow Gaussian function and turn it into a delta function. So we can now do that in 2 dimensions and define a 2-dimensional delta function. It really looks like this. The 2-dimensional delta function is the same as the product of 2 of the 1D delta functions. And just as in the 1D case, their transform in 2 dimensions is just the value 1. Finally, there's one more Fourier transform pair that we're interested in, and that is our friend, the sampling function. So now I'm going to have a 2D sampling function, and here's what it looks like. We're going to sum over we're going to sum over 2 dimensions. So m and n are going to take all possible values, and this is going to be delta of x minus m, delta of y minus n. We sum this over all m's and n's, and what that does is in the plane, so if we're looking down on the xy plane, there will be a delta function at every, in a square lattice of lattice size 1. So you can imagine this bed of nails sort of arrangement of delta functions in the plane as m and n take on all possible values. And just like in the 1D case, the Shaw function is another function whose Fourier transform is the same as itself. So Shaw of xy transforms into Shaw of uv. So those are all of our friends, the functions and their Fourier transforms. And I can show off a couple of them. So in this, I'm going to use this particular colored mapping of complex numbers, where real numbers are red when they're positive, green when they're negative. Imaginary numbers go from blue to yellow. And so as you move around here, you change the phase. As you move along the radius, the intensity increases as we increase the magnitude of a complex number. So here's the Fourier transform of a square. It's this product of sinc functions. And so you can see we have positive, negative ripples in the Fourier transform just coming from our friends, the sinc function. Here's the Fourier transform of a disk. So that's my circ function, and this is this Bessel function. All right, so with these, we have these transform pairs, and there are actually no big surprises here. The only function that's really new is this circ function, and it's the same kind of idea as the rect function. What about the Fourier transform properties? And the properties are interesting because there are a couple new properties that are made possible by the fact that we're working in 2 dimensions. The first one is the scale property, and it's really pretty close to what we had before. So if we make our function of x and y narrower, so we have a, b, g of a, x, b, y. So if a and b are large numbers, then this becomes very narrow in those places. That transforms to g of u over a, v over b. So just a generalization of what we saw there in 1 dimension. The shift property also looks familiar. X of g of x minus a, y minus b transforms into big G of u, v times a complex exponential e to the minus I 2 pi a u plus b v. So we have a complex exponential, a phase term that now multiplies what is otherwise just the ordinary Fourier transform of the function. So here's what that here's what that might look like. So here is my circ function, and there is its Fourier transform. And now what I'm going to do is I'm going to start shifting my disk, my circ function, along the x-axis. And you can see that what's happened is that in the horizontal direction, I now have new colors appearing. That's where the where this phase factor starts to apply. And if I shift now in the vertical direction, you can see again the colors are shifting in the vertical direction. And that's because I have a non-zero b, which is multiplying the v, the vertical coordinate in the Fourier plane. Now what happens if I move in a diagonal direction? Well, that way I'm going to have something that changes both with u and v. And here we go. And the farther I go, the faster and faster these phase changes occur. And if so as I go farther out, I get very, very fast phase changes due to this rapidly varying complex exponential. Okay, so another property that we really like and that we talked a lot about last time is the convolution property. So if I have g convolved with h, now these are functions of 2 dimensions, that just gives us g of u v times h of u v. So once again, we have this wonderful property that the convolution integral, which in this case is a double integral and is pretty tedious and computationally intensive to compute, well, its dual in the Fourier transform space is very simple. It's a point-by-point multiplication of the corresponding transforms. So let's look over here where I'm doing a convolution with a Gaussian filter. So what I have is an image. This is my kernel, my h of x, y, and this is the convolution of the two. And what's happened, of course, is that this kernel is a Gaussian and it's going to blur the image. Now the way to compute that, well, I can take the Fourier transform of the original image. I multiply it by the Fourier transform of the kernel. And what I get is a Fourier transform where the outer reaches, the farther out parts of the Fourier transform, that is the high frequency components, have been attenuated to near zero. When I transform back, I get this blurred, this lower resolution result. We can also do convolution with a sampling function. So here is my G. It's another one of these smiley faces. Here is H, which is a lattice. And if I convolve these two, I get copies of my original image at every lattice point. And I can do this in the Fourier domain as well. I take the Fourier transform of G, I multiply it by the Fourier transform of H, and what I have here then is, in the Fourier domain, samples, delta functions, at lattice points. But if I do the inverse transform, I actually get my original image back because the lattice that they are reconstructed on is big enough that there's no aliasing. So here's what happens if I decide that I'm going to sample my Fourier transform more sparsely. So this is a sparser sampling in the Fourier domain. The way I got it is I used a sampling function like this in the Fourier domain, which corresponds to a smaller lattice in real space. And so when I multiply this by this, get this Fourier transform, I transform back, I have my motifs too close together. They're overlapping, and this is a sort of aliasing where the information at the extreme edge of one copy of the motif is interfering with the adjacent copy of the motif. And so we have aliasing when we have sampled too seldom. Okay, so I'll put down the names of these properties, and we're going to have a couple new properties that I think you'll really like. This is scale, this is shift, this is convolution. Now here's another one. It's called rotation. And the rule is just this: that if I take a function and rotate it, I'll show you what I mean in a minute. That transforms to its Fourier transform is also rotated in a similar way. Okay, so here's what I mean. Here is my two-dimensional density, and I can describe it in the x and y directions. Now suppose I make a new coordinate system. Let's let the x prime axis be rotated by that much, and there will be a y prime axis that's rotated by that much. Now, if I do the Fourier transform of this, I will get some kind of thing in the u-v plane. It's usually some kind of pattern that looks like that. It turns out that if I change the coordinate system to x prime, y prime, that's rotated at a certain angle, then if I define a u prime and a v prime, which are rotated by the same amount, then this pattern interpreted in the new coordinate system is the same as the original pattern interpreted in the new coordinate system. So what I've written here is I'm saying if G is evaluated on a rotated coordinate system, then big G is evaluated on a similarly rotated coordinate system. Finally, there's one property that we are going to really like, which is the projection slice property. And it has to do with computing lower dimension projections from higher dimension densities. So what I could say is I'm going to define an operator that is going to be p sub y, which means a projection along the y direction of some density, and p sub y operating on my function g is going to be the integral of g of x, y, dy. So what I'm doing is that I'm leaving x unaffected, but I'm integrating along the y direction, and that gives me this thing called p sub y of g. So here's how I think about it. Here is my density. This is g of x, y. And if I integrate along the y direction, then what it is I just take all the density that I find along a particular line added up and sum up these densities as we take these projections through the 2D density, and we get a one-dimensional density that I'll call p sub y of g, and this whole thing is a function of x. So the really cool result is that a projection, p sub y, operating on g of x sub y, transforms to the Fourier transform of g with the v value set to 0. That is, instead of being g of uv, we have g of u 0. So it's I guess you could say the equator of the g function if you plot it in the uv plane. Okay, so I'm gonna go ahead and prove this thing. Let's start off with the Fourier transform of g of xy itself. Okay, so here's g of uv is, by the definition, g of x, y, e to the minus I 2 pi u x plus v y. So this is the definition of this is the definition of the 2D Fourier transform. Now, what is g of u comma 0? Well, it's going to be the same thing. It's going to be g of x, y, e to the minus I 2 pi u x, but vy is always 0 because here v is 0, dx dy. So we have a complex exponential that only depends on x, and that means that we can reverse the order of integration and get something that looks like this. G of x, y times e to the minus I 2 pi u x dy dx. And because we don't care about y anymore, I can move this dy in here. And you'll notice that what I have here in this box, which I'll make red because it's so cool, this is, of course, the projection of g. So this is p sub y g inside this box. And we're taking the Fourier transform of it, and that is now g of u comma 0 is the 1D Fourier transform of the projection of g. So if I transform this back, I get the projection of g. So what this means is that I can compute the projection of a 2D density pretty straightforwardly. Here's one way of thinking about it. If I have a 2D density, and let's suppose that this is the density of cross-section of someone's body, and we're going to take a CAT scan. And we're going to then compute a projection. We're going to look at the attenuation of X-rays as they pass through a slice of this person's body, and we get some kind of function that looks like this as a function of X. And so this is P sub Y little g of X. Now, meanwhile, we know that there exists a Fourier transform of this two-dimensional density distribution. So Fourier transform in 2 dimensions gives us some kind of density as a function of U and V. And we also know that the Fourier transform of this 1D thing will give us some kind of one-dimensional Fourier transform. So this will be U, and this will be P, Y, G. This will be the Fourier transform of that. So I'll write it like this: Fourier transform of P, Y, G along the X direction. And so what this theorem says is that the Fourier transform of this projection is the same as this density G of UV evaluated at V equals 0. So the quantity that we see here, this Fourier transform, has the same values as we would see along this line in the 2D Fourier transform. So this is the projection slice theorem. It says you take a projection of some 2D object. Its Fourier transform is the same as a slice through the 2D transform of that density. Now, this is not all that interesting except when we combine it with the rotation property. So what the rotation property says is, of course, we can take we can rotate, imagine rotating the person inside a CAT scan machine. So you rotate the person a little bit. Of course, we know that that will rotate the Fourier transform a little bit. We again do this projection along the y-axis, but we'll get a slightly different thing because we're projecting through the rotated person. We get this 1D Fourier transform, but we now know that we've rotated the Fourier transform. And so if we were to insert the new slice, the slice would be at a different angle, which represents the angle by which we rotated everything. And so if we rotate through all possible angles, we actually have a way to fill in all possible pixels in that two-dimensional distribution. So this allows us to do something that I showed you in the very first lecture, which is here is a two-dimensional density. Here is its two-dimensional Fourier transform. And what we can do is we take a projection in a particular direction. Here is that projection here displayed in a grayscale. We take its Fourier transform, and then we insert this Fourier transform in the appropriate place in the 2D Fourier transform space. And then we can compute an inverse transform, and we get a result. Now, in this case, the result is kind of interesting. I inserted a slice that looks like this. It's a delta function in the horizontal direction, in the U direction. And that, of course, converts into a constant in the X direction in the reconstruction. So what I've done is that I've taken this projection and now recapitulated it, but here it acts as if it's spread out into a beam or into a back projection, projecting back through that entire volume. So then the trick is that we rotate the object, or in this case, we rotate the projection direction, and we do this same trick, take Fourier transforms, and we insert them into different slices. And you can see that as we insert them into different slices, this sort of back projection looking thing begins to change its appearance. Then as we compute lots of these terms, we start to get better and better reconstruction of the original object. So that when we have inserted slices in a sufficient number of angles so that we have specified the value of voxels everywhere in the plane, then we can make a good 2D reconstruction. So up till now, I've been talking about the pure, beautiful, mathematical, two-dimensional Fourier transform. But in fact, what people always are using in image processing and in CryoEM reconstruction is something called the discrete Fourier transform. And it turns out that the notation and so on is a little bit messier, and so I decided to just tell you about the continuous Fourier transform itself. But the discrete Fourier transform is, on the one hand, a nice approximation. On the other hand, it actually is an exact transform in the form that you can transform from real space to Fourier space and back. The interesting thing about the discrete Fourier transform is that the formula looks almost exactly the same. We've just replaced the integrals with two sums. And the other thing that is interesting is that there is this division by n happening in the exponent. That informs the way in which we can scale the results of the discrete Fourier transform. So let me show you here what that looks like. Let's suppose that we have an image. This is an image of your favorite molecule. And let's suppose that we have sampled it with a pixel spacing of 1 angstrom. And maybe we have a 100 by 100 pixel image. And so we could say in the x direction or in the I direction by this, we go from minus 50 to plus 49 units, and our units are angstroms. So this is the calibration of the size of the image. It's 100 angstroms wide. Now, when I compute the Fourier transform of this, how do I label the axes of the Fourier transform? Well, because of this division by n in the formula, this is what it looks like. Over here is minus the Nyquist frequency, so this is 0.5 inverse angstroms. And this is plus the Nyquist frequency minus a little bit, so this is actually 0.49 inverse angstroms. And the spacing in the frequency, on the frequency axis is going to be 1 over n times delta x. So in our case, it's going to be 0.01 angstroms inverse. So this is how we can calibrate the Fourier transform of something that we know in terms of spatial frequencies, in this case in terms of inverse angstroms. We always go from minus to plus the Nyquist frequency, which is half of an angstrom inverse, and the steps are the same as 1 over the entire size of the original image. Okay, so the discrete Fourier transform is really cool. We can give the computer any kind of object and ask it to do a discrete Fourier transform, and we get back a result. And you would say, is there an equivalent amount of information in these two representations? Because I claim that we can do a discrete Fourier transform. We can also do a discrete inverse Fourier transform and get back to the original object. So we start out with, in this case, a 32 by 32 pixel image, and we get a 32 by 32 pixel Fourier transform. but each pixel gets a complex value. I'm displaying these in colors because there's both a real and an imaginary part of the numerical value at each pixel. So this sounds like I'm really kind of cheating, because here I have pixels that have only one number associated with it. Here I have pixels that have two numbers associated with each one, a real value and an imaginary value. So what's going on? Well, the answer is that there are symmetries in the real and imaginary parts, so that there is actually not any more information in the Fourier transform than in the original image. So here's the Fourier transform of the image that I just showed you. And now what I've done is I've split off the real and imaginary parts. Because this is the transform of something that was an actual real density map, you can show that the real part is symmetrical. It is symmetrical in inversion through the origin. And so you can see that for every red spot here, there's a red spot there, for example. The imaginary part is anti-symmetrical. That is, for every positive imaginary part here, there's a negative imaginary part there. What this means is that I could actually throw away half of the pixels in here and be able to reconstruct it, because I look at the real and imaginary parts and I do the appropriate symmetry or anti-symmetry to those quantities. Turns out that if you need to save space in a computer, you can work with half the number of pixels, but it's really nice to have all of the pixels there, because it makes the bookkeeping so much easier. Okay, so that's the 2D Fourier transform. It has a bunch of cool properties. There's a 3D Fourier transform, and you can see that it's exactly the same idea. We now have a triple integral. We start off with 3 spatial coordinates. Up here is the product of these of the 3 terms, and the inverse Fourier transform corresponds exactly. And it has all of the same properties: scale, shift, convolution, rotation, and the projection slice theorem. In the case of rotations, now we can not just doing rotations in a plane, but we can do the 3 rotations that define an arbitrary rotation in 3-dimensional space. And in the projection slice theorem, what it says is I can take a projection of a 3-dimensional object, which together is a 2-dimensional image, and that corresponds to a 2D slice through the 3-dimensional Fourier volume. So here's a summary of what I talked about today. As far as 2D Fourier transforms, here are the Fourier pairs that I talked about, and these are the properties that I described. Thank you.